Good morning, everybody. It is 11 a.m. on the East Coast on June 10th, 2022. I am coming to you live from a hotel room in Washington, D.C., and you are listening to Tales from the Heart, a podcast from the Hypertrophic Cardiomyopathy Association. We are live on Facebook today, and this podcast will be uploaded to the Stratosphere in the next couple of days, and you can follow us on all social media platforms. Today, I am joined by an old friend, a young old friend, who I've known for, I don't even know, 15 years probably. Who comes to us from the world of genetics. And that is really important because today is kind of a kickoff event for the HCMA. We're going to be spending the next 2 years discussing genetics at a very deep level, but we have to start somewhere. So as they say, let's start from the very beginning and understand what are genes and what are genetics and how did we get to where we are today. So without further ado, I welcome my co-host for today, Colleen Kalashut, genetic counselor extraordinaire. And I am going to ask her to tell you a little about herself and her history and how she came to this occupation. Good morning.
Thank you. Good morning, Lisa. Thank you so much for having me. I do remember the first time I met you. I think it was probably one of my first cardiology conferences right out of grad school. And then of course, going to your meeting in New Jersey. So I am a cardiovascular genetic counselor and a clinician scientist, which means that I both take care of patients and I do research. And I've probably seen more patients with hypertrophic cardiomyopathy than any other disease by far. I got my start in the field working at UCSF in San Francisco. And then a couple years after that, I moved down to Stanford and was the first genetic counselor in cardiology there, of course, very closely partnering with you and Ashley. And we built out a genetic counseling service in cardiology that is still to this day the largest genetic counseling team in the world, which I'm very proud of. And of course, first place we started with was hypertrophic cardiomyopathy.
Of course.
And it's probably still the disease we see more of, which is partly prevalence, right? It's more common than other cardiac diseases that are genetic, but it's also just so much further along, and it's where we had the center, a really center of gravity of expertise at Stanford. So I was there for a decade, building out this program and seeing patients and doing a lot of research around cardiovascular genetics. And then a couple of years ago, I made a leap from academic medicine to industry, specifically to work at a company that's trying to bring genetics to everyone, not just the people who can access the ivory tower or the Stanfords or the Mayos or the Clevelands or the Johns Hopkins of the country. So I joined Gene Matters, which was a telehealth and technology genetics startup founded by a genetic counselor, Jill Davies, and I was leading our cardiology service as well as our research program. And then in the fall of last year, we were acquired by Genome Medical. And so these two companies that kind of had very similar visions and missions came together, and I now head up research for the combined company. And still see patients. I will never stop doing that. It's my passion and something that just gives me so much fulfillment. So I still see patients in cardiology, including HCM patients all the time, and have really enjoyed the last couple of years sort of getting out of that very specialized, advanced academic medicine center, which was so fulfilling and we made a lot of difference, and instead focusing on what about everybody else and how do we get them both genetic testing and genetic counseling, and how do we do that at scale, and how do we accelerate how quickly families can access genetic testing. So a lot of my research now is not on cardiovascular genetics, it's instead like genetics wide. How do we get this to more people in a scaled, sustainable, but still patient focused, because that's who matters kind of way.
So you've seen a lot in your career. But things happened before you were professionally involved.
They did.
Some of those things happened maybe before you were even born, and maybe before.
Well, some.
So let's take this back 20 steps.
Mhm.
Let's talk about genes. Like we all know the term genes. 23andMe has kind of normalized gene testing. But what are genes, and can you give us a genetic counselor's explanation of what they are and why they're important in specific diseases like HCM?
Absolutely. And there's a few different ways to think about genes, right? Like genes are what we inherit from our parents and pass on to our children, right? We
Yep.
don't get all of our parents' genes. We only get half of each parent's genes, and we don't pass on all of our genes to each children. Each child only gets half of our genes. And when we say that we inherit things like heart disease runs in my dad's family, I got it from him, it's through those genes that actually come in those little packages of the egg and the sperm. You know, they're actually physically in there, and that's how we get them. It's also when we say things like, my family's very tall, those genes are what's contributing to that. So that's more the like human level way we think about it, but then there's like the biological level, right?
Mhm.
So genes are sections of our DNA that are a recipe for something, usually a protein. I don't mean protein like, hey, when you eat a steak, you're getting a lot of protein. I mean the actual little things in our bodies that do a lot of the jobs that our body needs in order to be a body, in order to function, right? So a gene is the sort of discrete thing, the little stretch of DNA that tells the body how to do something, usually how to make a protein. And when there's a difference in that gene, in a gene, that causes problems with what it's telling the body to do, then a genetic disease can form.
So if those problems, I think of them as spelling errors,
Yeah.
exist. So if it's supposed to be ABC, and we know it's not really ABC, but it's AABC, things are
Mhm.
confusing.
Yeah.
And it can't follow a pattern because it was supposed to go ABC and it didn't go ABC. So it sent it off in a different direction. I often liken the HCM gene mutations as the blueprints to build your heart, and they were just made a little wonky. It still makes
Yep.
the heart, but it doesn't function like a normal heart. It functions
Yeah.
differently.
Yeah. Another way
So
to think of it is the recipe, right? Like it's a recipe. And if you change a letter in the word egg, and that causes the person, your body, you know, using the recipe to put something other than eggs into the recipe, you know, your cake's going to come out differently than it would have if the recipe didn't have that spelling mistake.
So these spelling errors or these recipe errors cause things to happen that can be devastating and make a pregnancy non-viable, or it can be a little wonky and it can show up later in life. And that's our HCM, genetic mutations for the most part. So what is happening in an HCM of those that we know, and we'll dig into that a little bit more later. What is happening at the protein level so these genes don't know what to do properly? What happened?
Yeah. So a really key thing to know about, to think about that is something called the sarcomere. So most of the HCM that we can explain genetically it relates to this thing called the sarcomere. For those who haven't heard about it before, it is a very critical structure. Sometimes we think of it as a motor in our heart. So our heart is a muscle. Each cell in the heart muscle has many, many, many of these things called the sarcomere. And they actually are sort of like a motor, or the way that we actually get from a relaxed heart to a contract heart, to a relaxed heart to a contract heart. The sarcomere is the thing that's actually doing that work. And what we've come to understand in the last several decades is that for most people with hypertrophic cardiomyopathy who have an identifiable genetic cause, it's because one of the genes that is the recipe for one of the proteins in the sarcomere has a problem. And then at the sarcomere and heart level, it basically makes it too active. It's sort of turned on too much. It's too tight, it's too strong, which I imagine we're not going to get into today, but has been a huge insight because now we have, for the first time ever, an FDA approved drug specific to what's wrong with the sarcomere in HCM. So that's not necessarily about genetic testing, but they came out of the same discoveries.
Yep.
And they're groundbreaking.
So that contractile protein, that sarcomere mechanism is abnormal in HCM. So let's talk about the kinds of mutations that can occur, because they're not all the same type of problem. Can you talk about the different types of mutations that can exist? And for now, we're going to focus specifically into HCM rather than genes in general. So what kind of mutations are there?
So the vast majority of the mutations that cause HCM are something we call missense, which is one letter's changed to another. So it's not that there's a chunk of the recipe missing, it's that, you know, it says 3 eggs, and instead of EGG for egg, it says EFG, which then, through ways we don't totally understand yet, leads to that sarcomere being overactive. There is one gene, though, in particular, where instead of it often being a missense, a letter change, there's actually just a whole bunch of the recipe missing, and that's for MYBPC3. It's just, hey, we stop reading the recipe, and sometimes that makes the body just ignore the recipe altogether, or like throw out the weird cake that it makes.
So if you're missing this big chunk of information, that we think different mutations might lead to different types of disease, more intense disease, more impactful disease. I'm a myosin binding protein C by full disclosure. We all know where my heart ended up. It's in a box. So it worked for a really long time, and I love her for doing that, but she struggled for a long time. But when you're missing this whole chunk of information, that might be more impactful on somebody versus a more mild mutation. And then there are benign mutations. Can you explain what a benign mutation is?
Yeah, which then will get us into inconclusive ones. So I'm Canadian, and how is that relevant, Colleen? It's relevant because there are differences in spelling between America and Canada that don't actually change the meaning of a word. You know, for example, the word gray, do you spell it with an E or an A? It's still the color gray. So we actually, one of the most fascinating things we discovered, we as a field, not me, but genetics researchers, when we started sequencing lots of genomes, we discovered that all humans are full of just tons of these little spelling differences, most of which we think right now do not cause health problems at all. They're that gray, A or E idea. And this becomes important, and I'm sure we're going to get there in genetic testing, because if we find a spelling difference, do we know that it's one like you have that explains your HCM, or is it a gray one that isn't a problem at all? And how good are we at figuring that out?
Okay, so that's a benign. Then we get into, well, let's pivot for a second and talk about today's genetic testing. We have lots of companies. When you and I first started talking, it was like $8,000 to do 3 genes. And now we have industry sponsored genetic testing to help find all different types of diseases, not just HCM, but you start with an HCM, a thick heart, and you dig in and you figure out why is the heart thick through genetic testing. So tell me a little bit about the kinds of genetic testing that are being done historically and today, and then we'll talk into what those variants and what those interpretations can lead into. So we started with Sanger, and what was that?
So first of all, we couldn't actually read a gene for a really long time, even after we knew genes existed. We could track genes through families, through certain scientific methods in a laboratory, but we couldn't read every letter of that recipe until Sanger sequencing was invented. And that is a sort of chemical reaction that someone does in a laboratory, scientist does in a laboratory, that is very slow and very laborious, where they're kind of reading through on a gel, which is a scientific tool, each letter after letter. And it takes a long time, and you can only do one at a time, one gene, one person at a time. So then about 13 to 15 years ago, next generation sequencing, which is sort of like sequencing 2.0, think of it that way. Sanger was sequencing 1.0, this is sequencing 2.0, had been invented and had gotten far enough along in its development as an invention that we could apply it to genetic testing. And fun fact, in America, the very first disease to have clinical next generation by next generation sequencing was cardiomyopathy.
Okay.
Which is cool. I love that fact as someone who loves that disease. Anyway, so next generation sequencing, bigger, better, faster, more, less expensive, basically. So instead of just one gene at a time, you can do a lot of different genes at the same time. It's much more automated, it's less manual. We can look at genes that we could never look at before because they were too technically challenging. And it all costs way less money, and it's getting cheaper and cheaper and cheaper. So that has just dramatically changed how quickly we can discover new disease genes, how quickly and cheaply we can perform clinical genetic testing. So it's a big change. And cardiology really went there before, it's not even beyond cardiomyopathies, before any other specialty in medicine. We started doing these large panels with dozens of genes, while lots of other specialties were still just using Sanger and looking at one or two genes, and often charging more than these large next generation sequencing panels. I cannot talk about next generation sequencing in panels without making one comment that you may or may not want, which is bigger is not always better. There's market pressure for laboratories to be competitive by saying they have a big test. But what our research and others have found is that the vast majority of the other genes beyond the sarcomere and the mimics on those panels are just noise. They don't actually help people, and they can be very confusing for patients and physicians. So bigger isn't always better. We have to be careful about that. Or if you're using bigger, because frankly, it's almost all that's out there now, we have to be very careful about what we do with many of the results. So forgive me for that tangent.
No, I like that tangent because originally we did 3 genes for $8,000.
Yeah.
And we really know that there's about 13 heavy hitters in HCM. We'll just call them those. But most of the mutations are in 2 or 3 different genes. So that's where your bulk is. And then you got 1 or 2% in those other spaces. But these 100 or 150 gene panels, it can add a lot of confusion, and we still don't know enough. And today in genetic testing, in large HCM programs, we're seeing about 40% of those who have clinical genetic testing find a pathogenic mutation, and a bunch more find variants of uncertain significance.
Yes.
So that means 3 things. Number 1, it's more common to get a no mutation found result. Number 2, variants of uncertain significance are incredibly common and confounding. And number 3, some people get really useful information about what the pathogenic gene is in a family. So let's take those in chunks.
Yep.
Let's do the good news first. Pathogenic mutation.
Yeah. What is that?
Yeah.
Well, and I actually want to step back for a second because, Lisa, a brand new paper just came out that sadly changes that 40% number to 33. So the National Society of Genetic Counselors got a bunch of cardiovascular genetic counselors together. This was led by Missy Kelly, who has been in cardio forever. She's a lab genetic counselor who's just brilliant and has done HCM for her whole career. But there are a bunch of other great people involved. And they did a systematic review and meta-analysis. They pulled all the studies that have been published to date to really say, how often do we find a pathogenic variant? And when you look at it as studies that applied current criteria for interpretation of genetic tests, it goes from 42% to 33%. In adults specifically, it's higher in kiddos. But that's been one of the big bummers. I mean, there were a handful of years there where we all thought it was 60%, and I counseled on that, and we talked about it at conferences. And then we're like, wait, it's 40%. And now we're like, oh, wait, it's 33%. So it's not that the actual genetics in humans' bodies who have HCM has changed. It's that our scientific understanding and our methods for interpreting genetics have changed. So that was a tangent from what you actually asked me. So what does it mean to find a pathogenic mutation? So when I sit with a family and say, your genetic test found a pathogenic mutation, what I'm telling them is the genetic test found the cause of your hypertrophic cardiomyopathy as best as we can understand in science and medicine right now. And sometimes we're more confident in that than others. But what that means at a gene cellular level is when we were just talking about recipes and spelling changes, we found a spelling change that makes the sarcomere not quite right, makes the heart not quite right. What that means at a human level is I can say to the patient, this is why you have this. You know, this isn't your fault. You didn't cause this. This thing right here that you got in the sperm or the egg, this caused this. And we can also say a few things, though this needs to get better than it is right now. On average, people with HCM who have a pathogenic mutation identified on their genetic testing have worse disease than people who don't. Not like crazy worse, there's still a lot of variability among people who have a pathogenic mutation, but they're going to have more symptoms. They're more likely to have AFib. It starts at a younger age. They're more likely to have other people in their family who also have it. Family is huge. It's really why historically we've done genetic testing, because if I can sit with a patient and say, your genetic testing found a pathogenic mutation, not only does this explain why you have HCM, it gives us a tool to figure out if your kids inherited it, to figure out if this is going to happen to other people in your family. If your kids did inherit it, let's say your daughter inherited it, she might have HCM now, she might have it in the future, but she also might never have it because there are some people who carry it silently. And, you know, we're still working out what that is, but it could be 40, 60% of people. And it probably differs by family and differs by gene, but we're not smart enough to fine tune that yet.
But I believe we are getting enough data and enough families so that we can start to figure out why this is happening, why there is within a family different types of penetrance and disease.
Can we geek out on that for a second?
Go for it.
So in my mind, this is where genetic testing goes next, which is polygenic risk scores. Poly what, Colleen? Okay, our genome's a really big place. When we talk about Lisa's NYBPC3 mutation, we're talking about one gene out of 19,000-ish in Lisa's whole body. It's a lot of other DNA in Lisa's body. There's been a couple of papers just in the last year and a half, and more coming, that have basically shown us what many of us have suspected for a long time, which is if you take into consideration genetic differences all across your genome and kind of combine them in a really scientifically appropriate way to say, what are the rest of your genes do to influence what your HCM is like? That actually explains part of why some family members get it, some family members don't. It's more severe in some people, it's more mild in other people. It's not the whole answer, but it's a fair amount of it. And it could help us in the future when someone says to me, okay, I inherited it from my mom, but am I going to get it? I might be able to say, well, in addition to finding your NYBPC3 mutation, we looked across your entire genome to get a sense of whether you are in the lower or higher chance of getting it, folks. And fortunately, you're in the lower chance. It doesn't mean it's not going to happen. It doesn't mean we don't still need to watch your heart, but we can give you a little bit of reassurance that there's some stuff in the rest of your genome that's maybe protecting you. So
We used
We're
to
not
talk
there
about
yet.
these, we used to talk about them as there's got to be some disease modifiers in
Modifiers. Yeah.
modifiers. And I use my air quotes for those who are
Yeah.
just listening and not watching. But we're like, there's something else. So we just call them modifier genes. And we didn't really know what they were, but we conceptually thought that they were there for a long time. And
Yeah.
now we're evolving to a point where we can say, oh, you have this modifier and that modifier, that bodes well for you, or you don't. And okay, well, we're dealing with the real deal HCM here. So those are pathogenics. And when we have a pathogenic, somebody who has the gene that is linked to disease and they have disease and it's running in families, we can use that information to screen other family members to see if there's a risk of them developing or not. But what if it's a VUS? We hate VUSs.
Okay. We hate VUSs. Before we get into what if it's a VUS, let's talk about how common they are. That depends entirely on who you're testing and how big your genetic test is and which genes are on it. Forgive me, I don't have these numbers off the top of my head, but I can tell you if you only test the sarcomere and the mimics, the amyloidosis, Fabry, Pompe in kiddos, etc., Noonan, we don't get that many VUSs. Where we get a ton of VUSs is we do these big panels, which is mostly what most people in the United States are probably getting right now, because there's ways that it's easier to access these big panels, especially financially because of sponsored testing. So I recently dug into this literature for a talk that I was giving at the Heart Rhythm meeting a few weeks or month ago. If you're doing a panel, a cardiomyopathy arrhythmia panel that's like 70 to 100 genes, 75% of people will have at least one VUS, variant of uncertain significance. So buyer beware, patients, doctors, genetic counselors, they need to go into genetic testing just expecting that. And then what we also know is most of those happen in genes that have no connection to HCM, and they should just be ignored if the diagnosis is HCM. Okay, so I wanted to like level set with how often does this come up, but then let's get into like, what is it? So a variant of uncertain significance is any spelling difference we find in a gene where we don't have enough confidence, we, the scientific community, the laboratory, the specialist you're seeing, to say, I can call this normal, benign, it doesn't cause health problems. I can call this a pathogenic mutation, it causes HCM. That space in between those two things, huge space. However, again, most of that on these big panels is stuff that's never going to be a good suspect for the cause of your HCM. It's in some gene that has nothing to do with HCM. It's maybe in a gene that has nothing to do with disease at all, which is something the ClinGen group, an international collaboration, has been really trying to sort out. I helped with an effort that Jody Ingalls from Australia led a few years ago to look at all these genes that are on HCM genetic tests and say, which one of them is there actually good research studies to say, yes, this really is an HCM gene? And spoiler alert, most of them aren't that are on these tests. However, okay, so most VUSs I see in clinical practice, I tell the patient and the doctor, you can ignore this, set it aside. It's unlikely it's the cause of your HCM. If the laboratory starts to think otherwise, they'll let you know. However, if you get a VUS in MYH7, you know, big player in hypertrophic cardiomyopathy, that gene, and it's not seen in thousands, hundreds of thousands of people who are just out walking on the street, which we have that kind of data now, and maybe it's been seen in one other family, there's a really good chance that that's the cause of your HCM. And there's some stuff we can do together as a family and genetic counselor team, or as a genetic counselor to genetic counselor to laboratory community team, to get to the point of clarity about, is that the cause? So those are two different brands of VUS that in my mind are completely different beasts.
In my family, we are a private mutation, which means if you carry the same mutation as I do, you are related to me. We need to dig into that family tree and see where our relatives were, because something happened. So a lot of families have private mutations. And how does a genetic counselor go and prove that that private mutation is actually in the right spot to screw up the recipe enough to cause HCM?
Yeah, great question. Well, one thing we're discovering is a lot of people who we thought had private mutations don't have private mutations. It's just that we hadn't sequenced enough people with HCM to find the other people who have the same mutation as them. So that's one thing. And then whether or not those people are related to each other across the world or whatever takes this like advanced level of genetic analysis. You can't just order,
Right.
both of you spit for 23andMe or Ancestry.com and they'll let you know if you're related. But so a couple of things. If it's a certain type of mutation, we don't need to know that it's been seen in anybody else. So those NYBPC3, you call them loss of function or truncating mutations that just lose half the recipe, we can just run with that and say, this is the cause. We know enough about them to know that when that gene gets disrupted or in that way, it can cause HCM. But what about a missense variant or another type of variant? Say it's just that spelling change in the recipe. How do we figure out, is that the cause? So historically, back in the day, back in when you guys were found, and we had to do something called segregation analysis, which is just a fancy science word for saying, give me all the people in your family who have HCM. We're going to test them all for the same private mutation and see if they all have it. And if they do, and we can kind of get enough people in your family and combine that with other information we have, then we can be like, yep, this is the cause. Fortunately, that's not the only tool we have available now. So we have other tools, like for example, work from you and Ashley's lab when I was there, and I helped with this study done by a phenomenal at the time PhD student, Julian Homburger, as well as from other groups. James Ware's group has done a lot of this. Have told us about which parts of NYH7, which neighborhoods, or so let me continue with our recipe analogy. Which lines of the recipe, which sections of the recipe are more likely to have normal, benign differences or more likely to have pathogenic mutations? And we can factor that in as well. So that's one example of sort of newer insights that we have that can help us in figuring out whether or not that mutation is really the cause.
So we find out, that's exactly what happened in my family. We did segregation analysis. They pulled everybody together. We did all this cardiac testing. People we thought did have it, didn't. The didn't did. So, the echo, the EKG taught us a little bit, but then when you put it all together, we found out exactly who had it, who didn't. And we can go back to, the 1900s and we can track the family all the way back. So we know where it came from. Not every family has the ability to track 100 plus years. No. I could go back actually more than that. I can go back like 180 years and we can actually track it back to Ireland. So yay, my Irish ancestors. Thank you so much. And ironically, the family name was Hart, H-A-R-T.
I didn't know that part of your story. Oh,
yeah, the Hart family from Cavan County, Ireland. So there you go. I have all kinds of weird things in my history. So we know our mutation. We were able to track it. We're able to do genetic testing on others, and that's great. And that's working for us right now. No VUS for us. The VUS people, there's going to be a paper coming out soon that I actually helped on, which is the reinterpretation of variants and what do we do with that mess. That paper should be coming out in the fall, I believe. And it's just a thought paper of what processes we need as a country to institute about who's responsible, what does the relationship look like? Is your relationship with your lab and your doctor transactional, or does it have history? Is there a connection? Is it an enduring relationship? And who's paying for that enduring relationship? And there's a lot of logistics questions here. So we can, once that paper comes out, I'll invite you back to the podcast and you can tell us what we're doing right and wrong there.
No, I look forward to it. I used, when I worked at a different kind of setting where we were a lot of our mission was also research and defining best practices. We re-reviewed every variant whenever the patient came back to see their cardiologist once a year. So we had a genetic counselor. We owned it, but we didn't get paid for it. It was not sustainable. It changed lives. We found things that we said were pathogenic mutations, and now they look like they're benign. And we found things that are VUSs that now are benign, and periodically, it happens a lot less often, VUSs that turn pathogenic. I have no doubt from our experience and from the data that other groups have published that this is something that needs to be happening recurring. And there's literally no model for it right now. And yeah. Anyway, another one of my soapboxes you got me on.
I think we could probably put about 10 soapboxes on and keep jumping on them over the next year or so. And we can continue having these conversations. And I think they'll be, we'll enjoy the hell out of them. I hope anybody else listening will find them interesting.
Right.
And find that there's some policy issues here we need to talk about. So that's
big time.
Genetic counselors don't get reimbursed by insurance. That is just mind-boggling to me.
Well, it's not quite that simple. I mean, I've been paid by a lot of insurers for my work. What we don't get reimbursed by is Medicare. We literally legally cannot bill Medicare because there is a list that is controlled by Congress of what providers can bill Medicare. And we have been trying to get on that list for a very long time. And it is a very slow work in progress. And I'm grateful for all the many patient advocacy organizations, including yours, who have supported very actively that effort, because it is a huge barrier to access to genomics care for patients.
Absolutely. And then some insurance companies will pay for it, but some of them just, oh, well, Medicare doesn't see it, so we don't see it.
Exactly.
So they have something to lean on. So we have to do that. Another soapbox. So I know your time is limited. We have about 5 or 6 more minutes today. So I am not going to get into everything I wanted to talk to you about.
Yeah.
But we'll find a time to talk again on it. I do want to just take a moment to, we kind of did a ground level, what is genetics today? We didn't do a deep dive yet. That's going to happen over the next couple of months and years as we build everybody's understanding. Why do I want to build everybody's understanding? Genetic therapies are coming. Okay, they're coming. We already have one trial in Danon's disease, which is in the HCM spectrum disorder community. And these kids, when you're a young man with Danon's, you transplant or you die by 20. The moms develop dilated cardiomyopathy, and they have a very, very tricky course. And a lot of them go to transplant in their 40s or 50s. So it's a sandbox, if you will, to identify good targets for genetic therapies in Danon's. But because they're able to go in, and we're going to do a whole other series on that exact process, we're using those technologies. And right now there are 5 companies that I'm aware of developing genetic therapies for HCM. So yay, but everything's got a but. Are we ready? What do we know? What do you think? Soapbox is yours.
That is something that has changed dramatically in the course of my career, right? The first genetic therapy studies were done at the NIH, I think in the 90s, but it could have been early 2000s. I'm pretty sure it was the late 90s. And tragically, they led to the death of one of the early patients who was participating. And while that was tragic, I think many of us also view the complete stalling on genetic therapy development that happened after that as also kind of tragic. And in the last decade or more, the field has really made its way back to trying this again for a large variety of diseases. And there's insights from outside of cardiology that are happening for other genetic diseases that can benefit gene therapy in cardiology. One thing that of course makes our favorite diseases harder is the heart is buried deep in the body. I mean, the most success we are having right now with gene therapies are in parts of the body that are easier to access, because you actually have to put something into the relevant part of the body or organ that then changes the mistake in the gene, the mutation. So eye disorders, blood disorders are further along than organs like ours that are trickier, the heart. But there's a lot of really good, smart people working on this. So I'm curious to see where we end up.
I am too.
I mean, there are people looking at gene therapy as prevention for coronary artery disease for everyone, potentially, not just rare-ish. We know it's not rare diseases like hypertrophic cardiomyopathy. So this is a cross medicine revolution that could go so many ways. I mean, it's fascinating. And I suspect it's going to be a game changer for some diseases and not pan out for others for a variety of sort of very technical scientific reasons. And we won't know for a while, for probably a generation, which is which, right? Like some disease communities will have huge relief and others might have a lot of disappointment.
So part of why I'm starting with this very rudimentary conversation is I think in about 2 to 3 years, we're going to start talking about clinical trials in HCM genetic testing or genetic therapies.
Yeah.
And I want everybody to have good knowledge. I want people to be able to have informed conversations with the coordinators for these studies. And I want everybody to feel empowered to have those conversations. So I will be referring back to go listen to the podcast with Colleen, and then go listen to this webinar, and then go listen to that. And then here's the clinical trial information, but it's going to take us a long time to build all this curriculum, if you will. And this is step one. I know Colleen has a hard stop at 11:45 and I'm watching the clock very carefully. So I am going to thank her for joining us. I'm going to stay with you for a little while longer to talk about the Genetic Information Non-Discrimination Act and how that is protective over many of the issues related to genetic testing. So we're going to stay and talk about that, but I want to take a moment to thank Colleen for joining us. I hope she comes back for another version of Tales from the Heart and shares her knowledge and experience with us. So Colleen, thank you so much. I want to be respectful of your time, and I know you got helped.
Thank you so much, Lisa. This was really fun, and I appreciate you stopping us on time. If I was the one responsible for stopping us, we would keep talking because I just love chatting with you, and these are such important things. So
likewise,
I'm really glad you're doing this, and I'm happy to come back anytime.
Fantastic. You'll be getting an invite.
Okay, bye.
Thanks. Bye-bye. So I want to take the rest of our time together this morning to talk about the Genetic Information Non-Discrimination Act, a little bit of history, and a little bit of a display in advocacy. So back around the early 2000s, the Genetic Alliance brought a coalition together of organizations like the HCMA to come to Washington to talk about genetic privacy. We were all starting to do clinical genetic testing, and we wondered who was going to get access to our information and what they were going to do with it. So there will be some links provided to you about what the Genetic Information Non-Discrimination Act is directly from the government, but I wanted to give you an overview. So Colleen asked me, like, what did you have to do with this? I'm like, well, I showed it here in Washington, and we went to Congress and we banged on tables and we explained why everybody is going to eventually be found to have some kind of a genetic mutation. And if insurance companies were going to use that information to charge us more for insurance or deny us access to coverage, that disease would only be getting worse and patients wouldn't be able to get to new therapies and discovery would be halted. And it took a little while and a little convincing, and actually it took 10 years to get it to the finish line. And did we get to perfection? You never get to perfection in DC because you have to negotiate with people who have differing views. And we did get to a good negotiation point. So what does GINA actually do? It protects you from having your genetic information used for the purposes of rating a health insurance policy or a group policy and taking you out of being able to be insured. So it can't be used for that. It can't be used for educational opportunities. They cannot use your genetic information to deny you entrance into a school or use it as a method to disqualify you from a program. It can't be used against you for purposes of employment with a couple of codicils on that. Generally in the lay public, they can't use it. The federal government, on the other hand, is excluded. So military service or Secret Service can use that information for hiring purposes. So you do want to think about career paths when you're doing genetic testing. So it can't really be used in your job down the street at a company. They cannot use genetic information. Companies, insurance companies, employers, schools cannot mandate that you participate in genetic testing. That's part of GINA as well. The only things we had to leave on the table were life insurance companies and long-term disability companies. They can use that information for rating purposes. So a life insurance company can decide to charge you more based upon your genetic predispositions if they are available in your medical records. Long-term disability can do the same. There is a resource document here. I will tell you so 2008 was the passage of GINA, and there were a couple of attempts to overturn it. About 4 years ago, 3 years ago, there was an attempt to be able to use genetic information. There was a bill presented by, it was a Republican, I believe, congressman. I don't think it was a senator. I think it was a congressman trying to get a bill passed. It died on the vine. Nobody bit, and it went away. And I don't think the U.S. population has tolerance for discrimination on genetic basis. You can't change it. It is who you are, and they shouldn't be able to use it against you. So I think we're on safe footing. I don't think anybody's going to turn that around to do something else. So I have a couple of questions here that I'm going to address real quickly. Bonnie, if you're still with us, you have a schedule for genetic testing. You were diagnosed. So you're asking yourself, do you care which mutation you have? Well, yes and no. If you have an identifiable mutation, you can use it to screen other members of your family. You mentioned that you have no siblings and your parents are deceased, but there could be cousins, aunts, uncles that might benefit from that. And you say you don't want to, you have no children, and you won't. However, for people who might want to have children, there's a process called pre-implantation genetic diagnostics. It's not for everybody, but it is an amazing technology. You would use IVF to get to the point of pregnancy. So you would have the egg and the sperm brought into a petri dish. You would develop that out to a few cells, and then scientists can test those cells to see if they carry a mutation, if you have an identifiable mutation. If the little 10-cell embryo has the gene, you don't implant it, you discard. If it is clear of the mutation, you implant, and you can have a pregnancy with an embryo that is not carrying disease. It's not the right choice for everybody, but it is an amazing advance of science. And we've had a number of children born to HCM families, and they have HCM-free children. And that is a big relief to the family. That is an amazing contribution of science into our lives every day, and really why we developed genetic testing to begin with, so that we can stop diseases rather than keep them going. So it's an eradication of HCM in that family line. So does that mean that that child is free of HCM? Yes. That means that child can't pass on the gene to their child, et cetera, et cetera. So there's some really amazing reasons why you might want to do genetic testing. Additionally, if we start moving towards genetic-based therapies, we may learn a lot of other things about genetics and HCM, such as maybe you have a mutation that there's an easy genetic fix to, that you can have a therapy delivered that may normalize your heart function. This is a dream. Don't quote me that it's happening tomorrow, but there are scientific discoveries that say it might be possible. But if you don't know your gene, you would not be eligible for those trials, and it wouldn't be an opportunity that you could take advantage of. So knowing your gene may have a little value to you now, may have no value to you now, but may have value to you later. And these are discussions that you need to have with somebody like Colleen, an educated and amazing genetic counselor. And there are amazing services around. If you don't know how to talk to a genetic counselor, if there's not one in your program, there are telemed availability of genetic counseling services from Colleen's company and other companies. And they're cost efficient. They don't gouge patients. They're not trying to make tons of money off of this, but they have to pay for their services. So they are fee for service models. So on that note, I didn't get to cover every single thing that I wanted, but I'm going to have Colleen come back and we're going to talk specifically about the role of genetic counselors and interpretation of mutations and how they change over time. We'll get into a little bit deeper dive there. But I think Colleen and I could probably talk for 12 hours straight and still keep going. But I was happy to have her with us today. I ended up having to stay in DC because yesterday I was at a health policy conference with our friends at Patch. And then I had the Big Card Warrior tour last night and I wasn't going to be able to get home in time. So I stayed here and I'm like, well, I'll just podcast from DC as well. So I'm going to wrap up from Lisa's DC tour. If you're on our private Facebook group, I took a walk by the White House this morning when I went out for my morning walk. So you can go take a look at that footage and see what the White House looks like today, and a little bit of a tour of DC. And if you're listening to us on the podcast later, you can visit us online and see the content there. So I thank you for joining us for Tales from the Heart today. I hope that this is the beginning of a much deeper understanding of genetics within the HCM community. And I thank our sponsors for helping us get this information out. We have some new partners that we're going to be announcing shortly that are in the genetic space that are going to be amazing partners going forward. And we're excited to be collaborating with them. So much is happening here at the HCMA people. You've really got to see what's going on in the website. We've got so many new resources. We've got so many new partners. It's a good time for a bad disease like HCM. We have so much discovery going on, and I'm very, very excited about some of the potentials that are coming. But every potential has reasons to be concerned and to truly have you understand how you need to advocate for yourself. So programs like this and others are here to help you understand all of the variables of HCM and allow you to make good, educated decisions for yourself and your family, and to learn how to advocate for yourself in these spaces that are a little technical. So I thank you for your time and attention today, and I am going to sign off. Have you enjoyed this episode of Tales from the Heart? We hope so. Please visit us at 4hcm.org, become a member, become a donor, become a volunteer. Great news, everybody. HCM Academy is now available online. What is it? It includes online sessions, learning about hypertrophic cardiomyopathy, patient stories about HCM and their management, and an opportunity to join online live with an HCM specialist to go over the slides, ask questions, and dig deeper into your understanding and knowledge of HCM. All CME courses are free, and you can find them at 4hcm.org or at thehcmacademy.com. The Big Hearted Warrior Tour continues. For the latest dates, please check 4hcm.org. And thanks to our sponsors, Bristol Myers Squibb, Cytokinetics, Invitae, and Boston Scientific. Did you know discussion groups are available at 4hcm.org Monday through Friday? Almost every day you can find a discussion group, whether you're interested in learning more about ICDs, pre-myectomy, screening your family. There's a discussion group for you. Even if you just want to learn how to balance your mental health, we have that too. So please join us for one of our live discussion groups, moderated by a peer volunteer, and you can sign up in advance at 4hcm.org. Just check the calendar for events. Please contact the Hypertrophic Cardiomyopathy Association at 4hcm.org or by calling our office at 973-983-7429. You can contact the HCMA by email at support@4hcm.org. Tales from the Heart, a podcast from the HCMA, is made possible through sponsorship from Boston Scientific, Cytokinetics, Tenaya, Invitae, and Boston Scientific.